Good evening everyone and welcome to the session number 45 from the playlist of IIT-JEE main physics. The topic is how to find the minimum separation between a charge and a current carrying wire. And based on this topic I have one question for this session which is written here on this board. So this question has been taken from one of my books and the question is a particle of charge plus q and mass m is projected with a constant speed v from point A towards a current carrying long wire which is lying along the y-axis as shown in this figure. So we have to find the minimum separation between the wire and the charge particle. So here there is a wire which is lying along the y-axis. The direction of the current is shown in this figure by this arrow, and a charged particle is projected from this point A which is lying on the x-axis at a distance x0 from the origin, and this charged particle is projected towards this current carrying wire which is lying along the y-axis. So here let us say this is the x-axis, this is the y-axis. So the direction of the current is towards the positive y-axis like this. So I am using the thumb rule now. So by the thumb rule, the direction of the magnetic field on the right side of this current carrying wire will be given by the direction of these curled fingers. So the direction of the curled fingers is pointing towards the negative z direction. So the intensity of the magnetic field on the right side of this current carrying wire can be written as mu naught I divided by 2 pi x. This is the magnitude of the magnetic field at a distance x from this wire, and in vector form I will be writing it as minus k cap. Minus k cap means that that is the direction of this magnetic field is towards the negative z direction. And this is the standard formula for calculating the magnetic field due to a very long current carrying wire or conductor. So we have found the magnitude of the magnetic field due to this very long current carrying wire. Now I will be using the Fleming's right hand rule in order to find the direction of the magnetic force on this charged particle. So the charged particle is moving towards this origin. That is now in the case of the Fleming this right hand rule, this thumb will be pointing towards the direction of motion. This forefinger will be pointing towards the direction of the magnetic field, and this middle finger will be giving you the direction of the magnetic force. So like this. Now this is the direction of the charged particle. This is the direction of the magnetic field towards the negative z axis. So this middle finger is now pointing towards the negative y axis. So we can say that this charged particle is experiencing the force towards the negative y axis, or we can say that this charged particle will be moving in the xy plane. And if it is moving in the xy plane, then the z component of its velocity will be 0. So we can say that v square will be equal to vx square plus vy square, where vx is the velocity component along the x-axis and vy is the velocity component along the y-axis. So now here the magnetic force on the charged particle will be written as q v cross v. Now here v is what? This can be written as vx I cap plus vy j cap cross b is what? Mu naught I upon 2 pi x minus k cap. So from here I will be getting q vx mu naught I upon 2 pi x I cap cross this k cap, and there is a minus sign. Now we know that k cap cross I cap is equal to j cap. Now here I cap cross k cap will be equal to minus j. So minus and minus will be plus j. So finally here I will be getting j cap. And here I will be getting Vy mu naught I upon 2 pi x, and here j cap cross k cap will be giving us I cap. So this is the force exerted on the charged particle. Now from here the acceleration of this charged particle along the x-axis can be written as Ax is equal to Fx upon m, where Ax is the acceleration of the charged particle along the x-axis. So this is now Fx. So from here the Fx will be equal to Vy minus Vy mu naught I upon 2 pi x divided by m. So this is the acceleration of the charged particle along the x-axis. And now the acceleration is also given by A is equal to V dV upon dx. So the acceleration of the charged particle along the x-axis can be written as V dot dV x upon dx. Now we have also one more equation here, that is V square is equal to Vx square plus Vy square. Now if I differentiate this equation with respect to t, here V is constant, so I will be getting 2 Vx dVx. This will be equal to, I am just differentiating this equation with respect to t. So this will be 0 is equal to 2 Vx dVx upon dt plus 2 Vy dVy upon dt. So dt will also get cancelled out. Finally, I will be left with 2 Vx dVx, that is equal to minus 2 dVy. So this 2 will also get cancelled out. So minus Vy dVy. Minus yes. So this is another equation which I have got. Now, if I divide this equation by dx, then this is the Vx dVx upon dx is the acceleration from here. So we can write it, this is equal to Ax. So Ax is equal to minus Vy into dVy upon dx, and here acceleration is also equal to this value. So if I just from these two equations I can write Vy minus Vy mu naught I upon 2 pi xm, which this will be equal to minus Vy into dVy upon dx. So minus and minus will get cancelled out. Finally I will be getting Vy mu naught I upon 2 pi xm. This is equal to Vy dVy upon dx. From here, this Vy and dY will get cancelled out, and this equation can further be written as this dx upon x will be equal to 2 pi xm, dx upon x, yes, now 2 pi m divided by mu naught I dVy. So this is the equation which I have got by rearranging the terms of this equation. Now if I integrate this equation, I will be able to get the relation between this x and here what is x here means what I will be doing is, now I will be first of all now finding the limits of integration. So when x is equal to x naught, then Vy is equal to 0. That is, when this particle is projected from point A, then the vertical, that is y component of the velocity is 0. And finally, due to this magnetic force, this particle will be moving along the negative y-axis. So let us say, consider that the minimum separation is equal to x. So when the minimum separation is x, the velocity can be taken as v, that is minus v. Minus v means because it is moving towards the towards the negative y-axis. So the limits of integration will be, that is vy is equal to 0 when x is equal to x naught, and when the minimum separation is x, then the velocity is minus v. Now I will just simply integrate this equation, and we will be able to find the minimum separation between the charged particle and the current carrying wire. So the integration of 1 by x, this is equal to log, this will be log x to the base e, and the limits will be from x naught to x. So this will be equal to from x naught to x, and this will be equal to 2 pi m mu naught I. This is constant, 2 pi m is constant, mu naught is a constant, I is also constant. So finally I will be getting here the value as, and this is minus v. So I will be getting the value as minus v. So this can be further written as log e x minus log e x naught, and log x to the base e, log x to the base e minus log x naught to the base e. This will be equal to 2 pi minus 2 pi m v upon mu naught I. So this can be written as log e x upon x naught. This is equal to minus 2 pi m v upon mu naught I. So from here, I can write that x upon x naught will be equal to e to the power minus 2 pi m v divided by mu naught I. Or simply we can say that the minimum separation between the charged particle and the wire, that is x, this will be equal to x is equal to x naught e to the power minus 2 pi mv divided by mu naught I. So thank you very much for joining this session. Now in the next session I will be continuing with the same chapter, that is the moving charges and magnetism, and the topic will be different. So till then, have a nice day. Bye.